Hello, my name is Jonathan Peterson.
My name is Tin Tron.
Together, we worked with Collins Aerospace to produce a phase-change material heat exchanger. On the agenda for today, we'll begin with the problem statement, moving into the design selection matrix, which was used to produce a found design concept, then the ANSYS simulations and physical testing that were performed on this found design. We'll then wrap it all up with a summary. The problem statement was clearly defined by Collins Aerospace. We were tasked with designing, fabricating, and testing a functional phase-change material heat exchanger. A phase-change material is something such as ice, where when environmental temperatures change, the internal substance temperature remains constant throughout the process. We are also tasked with improving operational efficiencies and constraints as shown.
This is the design matrix that we use to select our final model for productions. In this matrix, there are three important criteria that we focus on: is the heat transfer per unit volume, the pressure drop, and the additive manufacturing difficulty. As you can see, the Cinnabon was the chosen model out of the selection matrix. The Cinnabon model provides intimate contacts between the PCM and the coolant. It is also simple, efficient, and printable.
Taking inspiration from the Cinnabon concept, we have here a spiraling inward passageway for which fluid will flow through. We also have these fins here used for heat transfer to the PCM. PCM will fill this space while water flows through elliptical passageways through the heat exchanger. Here is the full assembly with no sections to show coolant flows in through the outside, out through the center, and then PCM is filled through this top manifold, and there's an overflow in this bottom manifold. The main body of our heat exchanger was printed using aluminum. You can see this here. It was printed with the services of Form 3D Solutions. They helped us throughout the entire process from the initial designs all the way to printing, and they offered an extremely great deal on this printing process. On the right, you can see the final assembly, which includes plastic PCM manifolds, machined clamp rings, handcrafted silicone gaskets, as well as all the additional fasteners.
For our ANSYS simulations, we conducted internal pressure simulations within our heat exchanger body. This resulting in a maximum stress 40 times lower than our material strength. Next, we conducted a tensile yield strength simulations that produced an estimated yield load of 2,954 pound-force. For our physical tensile tests, the internal heat exchanger structure was capable of withstanding more than 12,000 pound-force without failure. The figures below illustrate the load applied and the stress experienced with respect to time. In the next slide, we have a video illustrate our test rig setup.
As you can see here is the completed phase change material heat exchanger. We have the top line, this line right here, this top line. This is used as the inlet loop. We have a flow and control valve right here. Water will flow from this cooler. As you can see, it's filled with water. There's a submersible water pump. It's a 60 hertz. At this height, about 5.42 gallons per minute is what kind of flow rates we're going to be getting out of this. So that'll flow into this loop through this control valve. Once it's opened, it'll hit this pressure gauge. It will then go through this thermocouple setup that we have here. The thermocouples are not connected as the heat transfer data is not important at this time. It will then flow through this top portion of the heat exchanger. It will spiral around. It will come out this second loop here. It will continuously flow through the other pressure gauge. We'll have an output pressure right back into our water containment. The heat exchanger test rig passed both water and vacuum leak tests with no noticeable leaks. However, we will need to redo the pressure drop test as the pressure gauges were not working properly. We will need lower scaled gauges as well as a higher powered pump to produce pressure drops necessary. In addition, this rig is ready to have thermal testing done on it.
Overall, our project was very successful. We completed some testing, however, further testing needed to be done in order to verify our concept.
We would just like to sincerely thank Collins Aerospace, especially Mark Zaffetti and Jeremy Strange, as well as Joseph Gabriel at Form 3D Solutions, and the whole ME department for their help and guidance throughout this entire experience. Thank you, judges.
Thank you.